This video will discuss Newton's method of numerical solutions, which is basically a way of estimating the value of a function at a particular point using a series of lines. So if we have some kind of function, this function is f of x, we can figure out what is the value of that function at a specific point using a series of lines. So let's say we want to approximate this function, although a line is not a good example for the entire function. We can start at one point, and in small increments, we can find the slope of that function and go a set increment. And in doing so, we can approximate the entire function by a line, almost like a digitization of the function. Because at each point, the function will have a certain slope, and we can go a limited distance with that slope while still staying reasonably close to the true value of the function. So the assumptions that we have to make here. So two assumptions that we have to make. And one is that the function is differentiable. So if you can't take the derivative of the function, you can't find the slope of it, and therefore you cannot use this method. And the second one is that your initial guess is close. For example, if we wanted to approximate this function, we need to get our initial guess close enough to this function that we can start in the right place. So we want to start like reasonably here. If we had, approximated the value here, saying that like, if this is the x-axis and this is the y-axis, and we're looking for the coordinates of that blue dot. So we shouldn't start it over there. We should start it somewhere reasonably close to the actual value of the function, somewhere that we know it works. Like maybe you know the y-intercept, or maybe you know something, have to know enough about this function if you know what the function is. So choose a reasonable initial guess. We can use this to solve for roots of a function. So let's say we have a function f of x equals x squared minus 31. So how could we find the roots of that function? So if we just draw, what is that? It's going to be a parabola because of the x squared, and it's going to have a y-intercept that is below. So it will be a parabola with the intercept at negative 31. This is the x-axis. This is the y-axis. So let's say we went to solve the roots. So we want to see, where does that function cross the y-axis? This is the same thing as saying find x squared equals 31, or square root 31 equals x. So you can do that on a calculator, but what is the calculator doing? It's doing a numerical solution. So you're going to be able to see what is the math behind how that calculator is solving your square root. Okay, so the procedure for this. First step is to make an initial guess. Next step is to calculate value of the function. So we want to see how close we got that function value. Basically, if we're solving for the roots, then we want that function to equal 0. So we're solving for that and that where y equals 0. Okay, so we had to calculate the function value. So we calculate f of x. We'll say initial guess x. Initial. Calculate function value f of x, see if it equals 0. Is it close? It's probably not going to exactly equal 0, but see how close we get. So then we would be able to 3 take derivative. So f prime of x. Now, actually here we want to say if f of x equals 0, then you're finished. If If it doesn't equal 0, then proceed with it. So take or calculate the derivative, and then calculate new guess. So that new guess, we'll say x1. And then we just sort of like repeat this process by calculating function, derivative, new guess, until we get to f of x equals 0. So I'll just say all right. So this is the procedure that we use. And the easiest way to do this is to do it in MATLAB, but we'll do it by hand and then we'll program it into MATLAB. So we need to set up a table that has our guess, our function value, our derivative, and then we can iteratively solve using this sort of guess and check method. Okay, so before we get into the example, let's take a look at this new guess formula. So we have x1, which is the new guess, equals x original minus the function divided by its derivative. Where here, this would be the function at x initial divided by the derivative at x initial. So all of those are for x initial. So then each guess, you kind of replace those things with the new ones. So where does that formula come from? Well, if we look at the formula for a line, so we're trying to approximate the function f of x at a specific point A. So f of x is approximately equal to f of a, so the original guess point, plus the slope of that function, f prime of a, times the increment distance, x minus a. Okay, so since we're trying to find a root, then we want this function here to end up equaling 0. So we want that to be 0. So we say that it is 0, and then we rearrange, and what we get is f of a equals negative f prime of a times x minus a. And then basically we need to solve out for x, and we get f of a over f prime of a negative plus a equals x. So this sort of translates to being x of the new guess, so n plus 1 being the new guess, equals xn minus f of xn over f prime of xn. So that is how we get what the new guess should be. All right, so now into the example. We are trying to solve this to solve the roots of x squared equals 31, or find basically what is the square root of 31. So the first thing we're going to do is make our initial guess. So we know that 5 squared is 25 and 6 squared is 36. So the square root of 31 is somewhere in between 5 and 6. So we can just guess 5.5. So we'll start out with just guessing. X initial, say, equals 5.5. There. So now we can calculate the value of the function. So we have guess x initial equals 5.5, and then calculate the value of the function f of x. So now f of x for x initial equals 5.5 squared minus 31. That equals negative 0.75. Okay, so not 0, but it is reasonably close. So we will now calculate the derivative. F prime of x, we take the derivative of x squared minus 31 is just 2x. So we have f prime of x initial, 2 times x initial equals 2 times 5.5 equals 11. So that is for our first time. So now we can pretty much set up a table. So we'll set up a table that has our guess, our function value, our derivative value, and then we'll keep going through that until the guess stops changing and f is basically 0. And so then at that point, we know we found the answer. We're close enough. So let's set up a table. All right, so we've got a table here and we'll start filling this out. So the first column is iteration. So our iteration 0, our guess was our initial one, so that's 5.5. Our function value is negative 0.75, and our derivative value was 11. So negative 0.75 is not really 0, so now we're going to continue the pattern and calculate what is the new guess. So the new guess, we have x1 equals x initial minus f of x initial over f prime of x initial. So we'll just say that x1 equals x initial, which is 5.5, minus f of x initial, which was the negative 0.75, so that'll become plus 0.75, and then divide by 11. So that comes out to be 5.568. Okay, so iteration 1, now we have 5.568. And so then we can continue and say that, okay, f of x1 is now the 5.568 squared minus 31. That equals 0.00465. Okay, so much closer. 0.00465. And then f prime of x1 equals 2 times 5.568 equals 11.136. Okay, so now let's do another row and we'll see how close can we get f of x to 0 and when does x basically stop changing. Okay, so here, basically, after 2 iterations, we pretty much got to where we wanted to be. Like, f of x came out to be 0, like 0 to 5 decimal places. So this is good. So now we know that square root of 31 equals 5.5678. And that is the answer. Okay, so that was actually not terrible to do algebraically, but some functions are a lot more complicated than just the square root. So if we wanted to solve the roots of a much more difficult function, we would use the same procedure, but if you do it in MATLAB and just using these same formulas in a loop, then it can be a lot faster to solve. So let's look at how we would program this in MATLAB.